everyone. Good morning, good afternoon, good evening from wherever you are joining us from. On behalf of the team, I warmly welcome you all to today's exciting session for this event. I'm thrilled to have you here as we embark on another remarkable quantum journey today. We would also like to remind you to kindly mute yourself. You can make use of the chat room to ask questions. And if you have questions as well, you can also use the reaction, raise your hand to draw attention, and we'll kindly ask you to unmute to ask your question. Thank you so much and welcome once again. It's been exciting from August with series of talks and lectures. And today we are excited because we are entering a new era where quantum science, with all its superposition and entanglements, evolves into cutting edges technology, shaping industries and advancing our world in unimaginable ways. And we are very fortunate to have a very resourced person as our speaker today. And his deep knowledge of quantum science will actually help us explore how quantum principles are being applied to develop real-world technologies. From the inference patterns of quantum particles to the uncertainty principles that changes our understanding, we'll learn how this fascinating phenomenon actually translates into groundbreaking technological advancements. So thank you all for being here and prepared to be entangled in this captivating and transformative session. Thank you and welcome. Kudos to our participants who have been very engaging and very active for all these months we started. Like I mentioned in today's talk, a new era from quantum science to quantum technology. I'd like to introduce our very resource speaker to us, who is in the person of Yusuf Karli from Cambridge University, UK, to take us through this session today. Karli, thank you so much for honoring our invitation. We warmly welcome you to our e-learning Africa International Quantum Science and Technology School. Thank you so much.
Thanks for this warm welcome and introduction. So I'm very, very happy to contribute as much as I can for this science and quantum technology development in Africa as well, because we are in the edge of another quantum revolution, what we call as a second quantum revolution. So today I'll try to explain as much as I can, like the state of art technology and what are we doing it. So let me share my screen and please let me know if I am Yusuf Karli. So I worked as a PhD student before in Austria and different universities in like different collaborations. I mostly worked on the quantum computation and cryptography, both experimental and theoretical perspective. And now currently I'm working as a postdoctoral researcher in the Cavendish Laboratory, working on the quantum networks. So my talk is actually divided to two sections. The first one is a brief summary of the classical mechanics and the quantum mechanics difference. We have to understand that part. That's very important because quantum mechanics is not disconnected from the classical mechanics, actually very, very connected. And the second section, so in the first section, we will go to the rise of the classical mechanics and the crisis that we have and the new paradigm, which is the quantum mechanics. And the second section, we will go into quantum technologies. What are the quantum technologies? Why do we need for them? And then how to have those kind of technologies in the real life, right? So the rise of the classical mechanics, of course, we start with the Sir Isaac Newton. So still considering the all happened things in the last centuries, I can briefly say that Newton is still for me the most important physicist of our history, because that started something it's like an avalanche. And then today we have the quantum technologies, but all will be nothing without a force of the classical mechanics. Of course, when we say the classical mechanics, I always mention the importance of Lagrange and Euler. So don't forget this all three is the is like the leader and the kings of the classical mechanics era. And then we have the classical mechanics crisis, the atomic scales and the light. So let's start. So Newtonian mechanics is, if we summarize a very simple way, that's that everything is point particles. We have a point particle A, point particle B, and then we have remote, very important word in here, instant force effect on each other, changing with an inverse square law. So we have force F equal something blah, 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 blah over R square. So that is very brief summary of Newtonian mechanic. As you see it in here, we do not mention anything related to time. So this F affects on an instant effect, remote instant effect from point A to point B. So then this mechanic is actually, we call it causal. So it's like there's causality and very strong determinism. Because if you know the equation of motion, like x and t, so if I know the function of the position with respect to time, xt, as you see it in his screen, let me just find my, where is it? Yes, pointer. Yeah. If you see this xt, so if I know the xt, all the dynamics, velocity, momentum, energy, everything is just mathematical operations of that xt. I can get derivative of that to get velocity. I can multiply velocity with mass to get momentum. I can just square velocity, multiply with m and get the energy of the system. So I know the energy, I know the angular momentum, normal momentum. Any dynamics I can imagine about a system only depends on the equation of motion xt. So it means if I know the t and x parameters, I can define the whole dynamics as fully deterministic behavior. So then we come to the Maxwell. So let's go with this little bit switch to the electromagnetic theory. So Maxwell has the wave theory. So we have an 8 differential equations for electric and magnetic interactions. That's also following the inverse square law. The force is still something, something, something over R square. And that's also causal and deterministic way. So there are very similarities between Newtonian particle physics and the Maxwell electromagnetic theory. That's why they are both classical mechanic. So the top of the classical mechanics. So actually everyone thinks that Einstein is the core of the quantum mechanics. Yes, Einstein is a very, very important figure in the quantum mechanics, early quantum mechanics time, of course. But Einstein, if we are going to give him a crown, we are going to give the pinnacle of the classical mechanics. That's the top where we stop classical mechanics. That's the Einstein part. So in the late 19th century, the Michelson-Morley demonstrated that the speed of light in vacuum is independent of Earth's motion and sun. So that's an experimental proof that the speed of light doesn't change with the speed or like rotation speed of the Earth, because the light goes the same speed, either Earth rotates that direction or the opposite direction of the travel of light. It doesn't matter. Speed of light experimentally confirmed as to be fixed and not changing with respect to motion of the observer. Then Einstein special relativity postulated two different postulates. First postulate is the law of the physics are the same from all inertial frames. Okay, so I cannot measure the energy from point A for an energy system of somewhere, and I cannot measure different from point B. I have to, the laws of the physics should be the same. And the second postulate, the speed of light in a vacuum is constant and doesn't change, depends on the motion of the source or the observer. So that's the theoretical background for the Michelson-Morley experiment. What we have it. So the crisis, the science follows in a very similar pattern of we do normal science as like the Thomas Kuhn scientific, like structure of the scientific revolutions. That book I can suggest to everyone. It's a very, very, very important book to understand what science, how science is happening. So the crisis that we have forces the science and current paradigm to be shifted to the new one. So the crisis of the classical mechanic happened in two important points. First of all, I should say that classical mechanic theory has not been abandoned. So we are using mostly classical mechanics to rule the world, right? So you do not calculate the quantum mechanics or very complicated stuff to do the car. Of course, you have like battery technologies, electronics, it doesn't matter. But most of the time, what we do is classical mechanic is still actively used in the daily life and in most scientific field. So the first crisis, the wave particle dilemma of light. So we know that everyone knows that. So light is somehow, sometimes acting as particle and sometimes acting as wave. So that was a very, very important discussion for a couple of 100 years, especially in the 18th century, Newton, Young double slit experiment. It was a complicated project, okay? And the crisis too, this is like a late 19th century because, okay, the classical mechanics works in a macroscopic level. It explains very well, the motion of the sun, motion of the earth, motion of the moon, motion of the planets and the solar system. Good. But in the microscopic level, theory doesn't work very well. We have some problems to solve there. So crisis why the light. So then in the 17th century, Newton suggested that the light is a particle because a very simple phenomena. You can think it, reflection and refraction. So light reflects from the wall and refract from the slits, right? But then in 1801, Thomas Young, showed an experiment. So we cannot object. That's 100% proof of the light is a wave. Young double slit experiment, which I will come to later. And then in the 19th century, Maxwell and Hertz took this double slit experiment idea and make it a very perfect, almost perfect theory that shows that light is an electromagnetic wave. So we know that the radiation, electromagnetic wave, magnetic fields, electric fields. So light is a wave, even like an electromagnetic wave. It's not only the color we see, that a microwave, any kind of the radiation is an electromagnetic wave. And but okay, everything was going good. Okay, light is a wave, But in 20th century, Planck and Einstein come with an idea that the particle theory revisited, I will say. So quantized energy levels are introduced by the Max Planck, and then Albert Einstein find the photoelectric effect, demonstrating the light also behaves as particles called photons. By the way, that's what Einstein gets Nobel Prize. He didn't get Nobel Prize for special relativity or general relativity. He got the Nobel Prize for the photoelectric effect. So Thomas Young double slit experiment. Everyone knows that when light goes to the two slit and we see that some kind of pattern behind it, is like some wave behavior, right? So that's a proof of like if two water waves or acoustic waves will show the same kind of interference, constructive and destructive interference patterns. So this is a very simple experiment, but we'll come to that one. It's like a problem. So the crisis, I'll go here, it's a crisis to the atom. In the 1911, the Rutherford, which is like one of the Cambridge professor in Cambridge, the structure of atom introduced. So what we know, so the electron circulates in orbit around an atomic nucleus, like a very similar pattern to the solar system of Kepler. So like close orbit in the core, but an accelerated moving electron. Accelerated moving electrons. That's a very important statement because we know from the Maxwell, accelerated moving electrons emit radiation, which is kind of like the source of the antenna technology, right? So we emit radio waves. we emit some kind of electromagnetic wave. So it means electron must eventually lose their energy because they accelerate and they emit photons and they fall into nucleus. So this was one of the critical problems of this closed orbit theory. How does it look? You all know from the high school physics, there is a nucleus, there are electrons around the nucleus, and the electrons are orbiting in the first excited state, like the first orbital, 2 electrons can occupy, and the second orbital, 8 electrons, and it goes like that. So then when electron does a jump between the states, for example, if you want to go from the first orbital to second orbital, you have to give energy equal to this separation of the orbitals. But if an electron goes from the second orbital to the first orbital, then it emits 1 photon equal to this energy separation. My dear friends, just you heard this, the sentence created the photonics quantum technologies. That's just it. An electron orbiting from a higher orbital and decaying from a higher orbital to a lower orbital, it emits a photon equals to energy separation of this E2 and E1, which is h bar omega. It's like the frequency of the photon, and the like Planck constant gives the energy of the photon. And that single photon is the core of the photonics quantum technologies. That's all what we are trying to target to achieve photonics quantum computation, photonics cryptography, and all other it. I'll come to that later in the second section, but just focus on this slide, the importance of that. It's been almost more than 100 years, and it created a new technology. So now when these two problems, the problem of the light and the problem of the electron around nucleus, that crisis is solved by proposing a new paradigm. So I separate them to the two parts: in the old quantum theory until 1920, and then the new quantum theory. In the old quantum theory, we have the Planck, black body radiation, which, if any of you interested, black body radiation is the first phenomena we couldn't explain without quantum mechanics. So that's kind of an interesting topic, not to focus on this talk, but you can note it. And then in 1905, Einstein, photoelectric effect. That's a very important phenomena. We introduced the photon particle. We introduced photons, like a particle quanta of light. And then 1911, Rutherford and Bohr atomic model, and then the Neil Bohr atom model you see in the previous slide. What we have it in here. So quantization is the core of the quantum words, quantization. So we have discrete energy levels. We have discrete angular momentums. We have discrete velocity. We have discrete positions. What discrete means? It means the electron around the orbit, around the nucleus cannot be in everywhere. It can be in a fixed, discrete, and pre-decided, depends on the system, distances to the nucleus. So first electron radius, like the Bohr radius, the first orbital radius, and the second one, etc. So the whole mechanic can only have specific values of energy, momentum, velocity, whatever you call. That was a quantization. That's what the source of the quantum mechanics comes. So this old quantum theory, of course, there are many contributed physicists, the Sommerfelds, Kramers, and mathematicians as well. You can also take a look later if you're interested. This old quantum theory. And then the new quantum theory, 1920 and later. So we have Austrian and German occupied fields here. So Born, Schrödinger, Heisenberg, Dirac, von Neumann, Hilbert. So even the first word of quantum mechanics was introduced by Born in 1924 in an article with a word, zur Quantenmechanik. That was the first time used quantum mechanics in a sentence. It introduced a new framework which required the new mathematical tools, linear algebra, Hilbert spaces, Dirac notation. That's all very mathematical and new mathematical perspective of physics. It's not like an analytical world, but it's like a linear algebra world. We have matrices, eigenvalues, eigenvectors. This all physics started to introduce a new explanation to the world, and it worked. So the foundations of the quantum mechanics experiments, if we give a summary, 1901, double slit experiment and discovery of radioactivity, and Thomson, of course, like great physicist of Cavendish, like a cathode ray tube experiment, discovery of electron, and then black body radiation. I mentioned the, of course, like Millikan oil drop experiment, which one of the simplest and impressive experiment for me. Rutherford gold foil experiment, and then for me, I always explain in this way in my lectures or in my other talks as well. The quantum mechanics is very easy to understand with a one experiment called Stern-Gerlach experiment, which I will go into details in the next slide. And then electron diffraction, and then de Broglie, of course, matter wave hypothesis. So we switch from is if light is a matter particle or wave, in 100 years, we ended up, guys, ladies and gentlemen, actually we are also waves. So like the matter has also wave in it. So this is the de Broglie matter wave experiment and the theory. So what de Broglie says, everyone was debating whether light is a wave or particle, and then he proposed a particle can also behave like waves, and this generated an experiment like called electron diffraction. So we see the same interference pattern similar to light. If you have a specific slit parameter and a specific electron speed and specific experiment that is hard to do, it's not easy as light, then you can also observe an interference pattern like wave, double slit experiment. So electrons shows like lines on the screen, which we will only see in the wave behaved system. But I should say that in here, there are some misconception make pseudoscience and false science and manipulating the people and using the scientific reality to for manipulative and for like bad intention pseudosciences. They say if you look at it will act different, and if you don't look at it will act different. I should state here, it's not look, it's observe. If I measure the electrons here, and if I want to see which slit they are going, that's not my eyes looking at the experimental setup. That's the measurement postulate. That's the observation by measurement changes the system, and you do not see this you do not see wave behavior, you see the particle behavior, because you are trying to measure electron, which slits, which path electron follows. It's not what I look with my human eye affecting the system. That can make some pseudoscience thing like bad eyes, evil eyes, etc. But I should say it here, measurement, not looking with your eyes. So the Stern-Gerlach experiment. This is the last part. Like before we switch to the second part, let me check my time as well. Okay, I'm going in a good time. So Stern-Gerlach experiment. What is Stern-Gerlach experiment? Is simply you have a magnet, North Pole and the South Pole. You have some magnetic field between them, and you are sending electrons from this right end to the magnets. So classically, when electron, because it has the dipole moment inside, right? So when electron travels through this magnetic field, classically we expect electron can go and can deflect in any direction, like you see it in the 4 line here. So classically we expect some scenario. If I repeat the experiment a million times, there is like a fluorescent screen here. I send electron and I look at the fluorescent screen where electron hits. If I classically, I expect to have something like line. I should see electrons in any vertical direction of this line. But in the quantum mechanics and experimentally, what we see, electrons either going up or down. So we see two sharp points on the fluorescence screen. Electrons either is in the top, either is on the bottom. That's called actually electron spin angular momentum. We know from the quantum mechanics, if you solved at any of time in your life, there's some like the quantum mechanics, like the infinite square law, or so like some infinite square wall, or any kind of like this spherical quantum mechanics solution. You remember that there's an m plus 1 over 2 minus 1 over 2. Okay, so that plus 1 over 2 and minus 1 over 2 is actually here that you see in the experiment. Plus 1 over 2 is the spin angular momentum of the electron, and it goes up, and the minus 2 is the spin angular momentum of the electron goes down. And then the quantum mechanics suggests that until you measure the electron, you have the superposition of these two spin. So your state, your wave function, is the superposition of two spin combination. Let's go to experiment. What is interesting, I think this will be an interesting experiment if you didn't hear before this experiment. So electrons here on the left, it can go up after the magnet. I simplified it, and it can go down. No problem. I send my electron to the magnetic field, and then I observe 50% of the probability my electron goes up, 50% probability of the time electron goes down. It means if I repeat this experiment 100 times, 50% of the time, 50 times, I measure electron goes up, and 50% I measure electron goes down. That's called the superposition, what quantum mechanics stated. Electron is in a superposition of going up and going down. But if you look at it in an experiment, I took it from like Wikipedia, not my modeling. So the source, electron source, we are sending in a ZSG apparatus, I will call it. This is Stenger-like apparatus, that's like the magnetic field system. So the electron, let's say, one electron can go up or down. So I block the electrons go down. And I took electron goes up and send it in another Stenger-like experiment, and that electron goes always up. So the electron goes up, down, and electron goes still up. There is no down. That makes sense, right? Why should you expect the electron goes up from the first magnet should go down from second magnet? But if you just send this electron after going up to the magnetic field or Stenger-like apparatus in the x-axis, like rotated 90 degrees. So now you observe that up and down change. So you have a different reference frame, right? You have a different measurement base in more technical language. Then this electron can go right or left. Okay, that makes sense because it was going up and now it can go right and left, no problem. Okay, so then if you take the electron goes up, then it goes right. Okay, no problem. Then if you send that electron another Z-oriented magnet, you see that sometimes it can go down. How that happening? How this happening? That electron was going up in the first magnet, in the Z magnet, and then going right in the X magnet. But when you send another Z magnet, you expect that they should always go up. But sometimes you see the electrons going down. But if you repeat this one many times Z, if you send the electron without sending X between two Z, that will always go up, 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 up. So that's kind of the measurement on X, remove the information on the Z. So that's something, the pure proof of quantum mechanics in the experiment for me. That was an early experiment time, but it's a very, very strong proof of the superposition, and it's the quantum measurement postulate. Okay, summary slide of the first section. Classical mechanics. What we have a particle m, and we have the equation of motion. We know the where is going to be particle at any time t. I know that one. So That's what we have classical mechanics and we have the whole dynamics. But we got the quantum mechanics. We have something called wave function, psi. So that psi has xt. Wave function is very simple to understand. Not the wave function itself. It will be, I don't know, like every like last couple of years, I have discussed this topic, what wave function is, from like bachelor level students to the Nobel laureate Anton Zeilinger and Serge Horesh and Rainer Blatt, etc. So still, that's a question, what's a wave function is. But as physicists, we know the absolute square of wave function, so the complex conjugation multiplication and like taking a square, of course, like not normal square, but complex square, absolute square of wave function. We know that very well. That is something we have full power and full knowledge on it. There's absolute square of psi, meaning one thing: the probability of particle being at position x at position t. That's it. That is the what wave function helps us. Anything within quantum mechanics is absolute square of wave function. Probability of particle being x and t. So let's apply to here. If the wave function at point A, that's a probability, some number. I didn't put it here. It's just like a random drawings. So it means if I put here A, if I calculate the wave function for A, I will get it. Okay, I have a probability of particle being at A at the time t, even if it's not time independent, it's time related. And it's the B is the C. And if you look at this integral from x to x prime, you will find that the whole probability of particle being between x and x prime points. And if you put this x to the minus infinity and x prime to plus infinity, what's going to be result of that integral? 1. It has to be 1 because that's the probability of particle being somewhere at any time t. So that should be 1 because that's the probability. If it's not 1, it means like there are some scenarios the electron is nowhere or a particle is nowhere. It's not acceptable. So we call this one normalization of the wave function. That has to be equal to 1 because a particle has to be somewhere. So that's what quantum mechanics tell us, all probability. And if you look at this wave function before, not wave function, that's square of the absolute square like wave function, what can we say? We can say, if I measure this electron, most probably I will find somewhere between this A and B. I will say there is a very low probability electron being at B. It's a very low probability, or C. If I repeat this experiment million times, I'm just making up the numbers, I will 500,000 times, I will find it in around here. And 200,000 of times, I will find it something here. And the other times, I will find B, C, even like D, E, like this is like an infinite line, of course, and all the possible spaces. So find it. So that is what quantum mechanics is, and actually that's how nature is. I'm not sure, maybe quantum mechanics will be disproven many years later, but until now, until today, it's always survived in any test. So that's the mechanism, that's the mechanic, passed all the tests we have done until now. So now we come to the second part, quantum technologies. So now you know what the quantum mechanic is. So we have this probabilistic nature of the systems. And that probabilistic nature and the superposition, most importantly, is the core of the quantum technologies. So what are the quantum technologies? Why do we need for them? And how to have them? Let's start. So I'll give 2 examples because they are my expertise area. So the photonic quantum computation on the left, that's a quantum computer will solve everything we physicists commercialize as, we physicists advertise as. Even that's what we say to everyone: the quantum computer. We need to have quantum computer because it's super strong, super fast. It can do everything that a classical mechanic cannot. Classical computer will take a million years. Yes, that's all true, no problem. But we need to understand how, because we need someone put their hand on the quantum technologies. As far as I see, there is more people speaks about the importance of the quantum technologies than more people is trying to achieve quantum technologies. So there are conferences I saw, hundreds of people speaks about quantum technologies and their importance, businessman class. I didn't see one physicist or one engineer inside them. It's full just the importance and the funding stuff, blah, blah, blah. That's also important. But then as a physicist, we have still many, many technical, fundamental engineering problems will take decades to solve to reach practical photonic like practical quantum technologies. That's why we need more people focuses on the lab, on the theory, on the simulation, on the calculation. Also, we need that people advertise the importance of the technologies and making industry and society ready for this big revolution in any way, like the mean, like economical perspective, political perspective, bureaucratic perspective, even ethical perspective. That was there was a ethical quantum program, quantum ethic program in the University of Innsbruck. I think they started a couple of years ago. So there's an institution focused on the quantum technologies, ethic of the quantum technologies. Okay, that's important. But we also need successful and dedicated persons work in the laboratories to achieve these technologies. They are not going to come from space. We have to find them. We have to generate them as humanity. We have to build them. It's not going to come from space with a spaceship. So let's go with the quantum network and cryptography. I love it. So we have to understand why we need quantum cryptography and quantum computer. That's the thing we have to understand. Modern cryptography. So modern cryptography based on complex mathematical algorithms, hard to solve, hard to break, and classical computers will take thousands of years to break them. But how do they work? Why it's a hard mathematical question, and why quantum mechanics or quantum computer can solve this mathematical problem? If you see it in here, it's not about technology, as you see, right? This is about still fundamental science. It's about mathematics and physics. Why quantum mechanics is important, why quantum computer is faster, is about physics and mathematics. It's not about some weird atom we find that has a super strong powers like in the Marvel movies. No, it's still mathematics behind it. So the simple example of an encryption, what encryption is, I always say the first encryption was found in Africa, probably because it was a language, right? So like the two different communities try to speak each other, but they want to speak each other secretly. What I do as a Turkish origin, if there is a Turkish guy next to me, if I want to speak something private, I will choose to use Turkish. If I'm sure we are the only two persons speaks Turkish in that community, I will use my mother language to communicate secretly with the people. So, but if you go in another example of encryption is a Caesar example, like the Caesar cipher. So this is very simple. You have the text hello, and then I'm shifting each letter with a 3 letter next to it. So H become K, E become H, L become O, O, R. No problem. Now I have a text, something Khor, no meaning. But if someone knows my shift parameter, they can just reverse it, right? Simple. Get this Khor, reverse by 3, you will get the hello. As you see it in here, this is not a very secure way of communication, but it was practical by the time, a couple of thousand years ago. Then you have a little bit advanced example, Wegener cipher. In this one, we are encrypting a sentence, a word with another word. So attack at down at the lemon. So we have the attack at down. So A, you have the chart on the left. You go to A and find the L here. And then you just encrypt with that in L. You go to T with the E. You find the T on the chart on the x-axis. You find the E on the y-axis. You just combine them. You find X. And then you have a encrypted text, LXFOP, blah, blah, blah. No meaning. But if you know the key, you can just match it and find the attack it down. That's perfect, simple, and you can use it in your real life to make some fun with your friends if you have some kind of secret message. It will still take a lot of time to solve this kind of simple encryption as well. So, but did you notice one thing here? I'm repeating this key, right? Because my text attack it down. Let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, let's say 11 letters. And my encryption key lemon is 5. It means I have to put more lemon next to lemon to encrypt my plain text to get this encrypted text. I will repeat my encryption key. That is the point. This is where we need quantum cryptography, because any key repeats in an encrypted text. It's always open an attack called frequency analysis. On the left, you see an encrypted text, no meaning. But what is the most common letter in this text? Most common letter is J. And if I know this text is based on English, I need some information, right? Some social information. And if I just say, okay, what is the most common letter in English? It's E. Okay, what happens if I try to solve the encryption by making connection between J and E? I have the whole text. I just made the frequency analysis. Most common letter is J, and most common letter is E, and I solved the whole message. This course aim to provide you with detailed knowledge of blah, 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 some text. That's why that frequency analysis is the way how to solve an encrypted text. That was the thing happened in the World War II as well, with the Enigma machines, for example. So this was kind of the way, and still is a problem. So there is a one way to avoid this problem, and it is it is to be one-time path encryption. It means I have a text and I have an encryption key, and the text and encryption key has the same length, and I'm not repeating that key anytime again in my life, anytime. So for example, if I meet with Henry, I hope one day, so we can just make 1,000 letter of encryption key and go to different part of the world, and then use that 1,000 letter of key for the next 1,000 letter we want to communicate secretly. No problem. But the problem, how can I make a secure, and that communication is 100% secure. No one, even the quantum computer, cannot attack it, because that was a randomly chosen key for randomly chosen each letter. You have a full random connection between each letter. The key doesn't repeat. We are making 1,000 letter encryption key and using it for 1,000 letter communication. But what about the second 1,000? If I have to repeat that key, that communication is not secure again. But the question, how can I make a secure communication with Henry from Cambridge to Ghana? That's a problem. That's a very big problem. We cannot use WhatsApp. That goes over America. We cannot use any internet or any already unsecure communication platform to make a secure key between us. So what can we do from a distance? Let's say where we are going for the lunch, and we have public message and we have the key, so we don't repeat the key. If key repeats, that will always not secure. So here, the quantum cryptography comes to place. Unbreakable encryption. It is not based on complex mathematical structure. It's based on quantum mechanics. It's based on the fate of how universe do something, right? But how? Simple, single photons. So we go back to the first part of the slide where Rutherford introduced this, Rutherford-Bohr atomic model. So I think we should always call Rutherford-Bohr atomic model, not Bohr or not Rutherford atomic model. That's my personal perspective. That's electrons moving between these orbitals is generating single photons. And that's the only single photon source we have. There is no other single photon emits from anywhere. So any light bulb or any laser, nope, LED, nope, they cannot make deterministic single photon like generation. So because how and why the single photon is safe? That's a very important theorem of the quantum mechanics, no cloning theorem. So this no cloning theorem says us as a quantum state cannot be copied. You cannot make a copy machine for a quantum state. That's all. That's it. I mean, I have the mathematical proof somewhere. It's not a topic of this talk, it's too much. But the issue, if I have a quantum state, no one can copy it. That's done. So it means if Alice and Bob and Eve, so if Alice sends a one photon, that's a quantum state. One single photon is actually a quantum object, simplest quantum object. This one single photon with properties of polarization, that's the qubit actually, then not the photon itself, but the photon carries an information, is the information, not the photons itself. Polarization, let's say. And if Alice sends single photons to Bob, quantum mechanics says there is no copy machine can make a copy of this single photon with the information in it. It means this photon will reach either Eve or Bob. It cannot reach Bob and Eve at the same time. So if I have a single photon source, and if I'm sending to someone, and if those photons reach to that person, I am 100% sure that no one has listened our communication. That's the simplest, pure theoretical explanation of cryptography. Of course, in the real life, its practice is different because generating this quantum states with a perfect quantum behavior is not that an easy task. That's what we are all trying to do it, right? So this photon will reach either Bob, either Eve. It cannot go there at the same time. That's, you trust your communication by the nature. It means if I send 100 photon, and if Bob measure 100 photon, and if I'm sure, pressure, I have to be sure my photons are single before, then I can say that, okay, I sent 100 photon, like Bob measured 100 photon. No one has listened to our communication. That's done. But we have losses, right? So we have to make error correction, loss correction, because when I set 100 photon naturally, even if no one is listening us, some of the photon will be lost because of the fiber, because of the atmosphere, because of the component. Even detector efficiencies are not that 100%. No photon detector can do 100% efficiency. What we have, state of art, very expensive detectors, like $1 million like $1 million of price, 80%, 85%, 90% maybe. So you have a natural losses. That's why in practice, I say it's still a problem. There are still very quantum hack papers. So I mean, just a couple of days ago, I uploaded some paper to an archive with my colleagues from Berlin University. You can take a look at that. We are investigating this quantum scenarios where how hacker can get information from our system depends on practical imperfections on the experiment, not the theoretical one, but the practical imperfections still leave some way for hackers, quantum hackers, to steal information from your system. So what's a single photon? We spoke a lot of single photon, but you might think that's very easy, right? Come on, Yusuf, what's this all 1 hour of talk with like a monologue with single photon, single photon, single photon? Okay, but would you be surprised if I tell you to get a single photon, high quality single photon every time when I press a button requires the most advanced technology we have and most advanced science we have. To generate a single photon pressing a button, you need the technology, the latest technology and most expensive technology and most expensive and latest science devices to generate them. Yeah, going from million photon to one photon is not an easy job. Let's see why. So what's a single photon? You see here a camera detection angle. Sorry, camera detection axis in the time axis. And I choose a delta t interval. That's my camera, let's say, resolution. I can measure a photon every delta t interval. Because why? I mean, if you some of your electronics or some engineering based, you will understand what the detector does. Gets a photon, create an electric signal, and we just understand there's a photon with the signal. But the signal says raising time, dead time, connections, BNC cables, lots of electronics, lots of chips, and these are limits our time. I cannot say I can choose a 10 to the minus 45 second time interval. No, nanoseconds, picoseconds, what we have in the current technology. Okay, so for example, the detectors that I am using has a 10 nanosecond at that time. I can only measure another photon in the next 10 nanoseconds. I have to wait. So I choose a delta t interval, let's say 10 nanoseconds. I want to have one photon all the time. If you look at the first source, I have 3 in the first delta t. Nope. I have 0 in the second delta t. Nope. If you look at the second one, I have 1.5, let's say one photon, okay? Mostly one photon, but also 0. When I say true single photon source, I mean every time, so simple. I'm a billionaire, let's say, I'm asking a device, give me a device. When I press a button every time, it will give me one photon. It means I cannot even tolerate losses as well. It should be always a one photon. This is a pure background in physics, actually, very complicated. You have to look at the Introduction to Quantum Optics books, last chapter, to understand the photon statistics, Poissonian, sub-Poissonian, number state, Fock state. This is actually a thermal source on the top you see. And the second one is a coherent source, a laser source. And the last one is the true single photon source. But as an experimental physicist, and I'm making a talk to people from different fields, different levels of different fields, let's go very, very simple, right? Because that's what at the end, this 20,000 lines of physics calculation end up with this one photon each delta t interval. But how am I going to prove that's a single photon? Of course, I'm sure most of you will believe if I say I have a single photon source. You will say, okay, I know Yusuf, it's like trustworthy guy, and I trust him. But the science doesn't work like that. You have to prove to the journal editor and journal referee that you have a single photon source. Otherwise, I can just say I have a single photon source. So let's look at the simple Humbury-Brown twist setup experiment, which is the simplest way of proving a single photon source. I have a beam splitter. That beam splitter is just a glass, some kind of crystal, reflects 50% of the light and transmits 50% of the light. This is actually a glass, as you see in the windows. It's the same glass, because when you look at the window in the night, you see a little bit of yourself and you see a little bit of outside. That's partially reflective and partially transmissive. That's the same. Just this beam splitter precisely manufactured to be 50-50 amplitude in the reflection and transmission. So if I have 100 photon source, if the photons are coming as a bunch, what do you expect? Sorry, I forgot to edit in here, the other example. If 100 photon comes, 50 photon will go detector 1 and 50 photon will go detector 2. No problem, half. But if you come with a single photon, that photon will go either detector 1 or detector 2. We are speaking here, if you notice, full particle behavior of the photon. I'm speaking as the photons are spherical particles, because if they are wave, they will go both direction. It's, as I said, it's not that simple, quantum mechanics. There's always wave particle duality. If you look at from a particle apparatus, you will see light is a particle wave. Sorry, it's like a particle. If you use the apparatus of measurement as wave apparatus, you will see it's like a wave. If I send the single photon to detectors, they will act like a particle. If I send the single photon to slit, I will see wave pattern in the background. It is wave particle duality. It's always there, but I can measure either particle or wave. That's what we call the measurement changes the something, right? So now I'm measuring as particle. I cannot measure two photons at the same time in both detector. I have one single photon. Either I will measure at detector 1, either I will measure at detector 2. So, and if I compare, this is one of the results from our paper from Universität Innsbruck. So if I compare the time difference between detectors, if they are 0, forget about these coincidences because it's like a time tagging a comparison. So if I look at the time difference 0 between detector 1 and like detector 2, I get 0 times correlation. It means the photons either here or here. That's the proof of perfectly prepared single photon states. If your photon is not single, you also expect some peaks on the center with the same height in here. That's how we do experiment. But forget about this plus 20 and minus 21. This 0 time delay shows that there is no correlations together with detector 1 and detector 2 when the time is 0. Okay, so to realize quantum photonics, I always say we need 3 main things. The efficient fast photon counters, that's not my expertise. Fast electronics and the photonic circuits, that's not my expertise as well. On-demand generation of identical single photons. Now we are going to say, come on, Yusuf. You were just speaking and giving a speech about single. Now you just said an identical as well. What identical means? Identical photons means anything you can imagine in a photon, either polarization, energy, spatial mode, they all have to be same. That's a single photon. Identical photon. So how can we measure it? It's the same experiment. We have a once very important quantum mechanical experiment. I would say one of the most quantum thing I have ever seen in my life. So if 2 identical photon comes to beam splitter from different ports, we have one single photon comes from the left port, and you have the other beam splitter, other photon source coming from the bottom port. These photons can reflect and transmit. Normally you expect like a 4 scenario, right? You expect the photon can go up, first photon can reflect, second photon can reflect, they can go different direction, both direction. No. Quantum mechanics states that if 2 identical photon comes to beam splitter at the same time, they have to go somewhere. That's the quantum interference, Hongo-Mandel effect. They have to go at the same detector. It means the 2 photons will go up or will go right. And if you repeat the same experiment before, you will also see if your photons are indistinguishable, identical photons, they will go the same detector, not different at any time. That's the core source of this photonic quantum computation. Here you see one of the Nature paper of 2020, the first quantum advantages using the photonic system, calculating a problem, like Gaussian boson sampling problem, which will take thousands years with the strongest classical computer we have. But in China, Cha Yong-Lu and Zhao Wei-Pan, they have demonstrated this with a identical single photons. And this is how it looks in the optical table. Guys, believe me, I wouldn't. Wow, I see here 10 PhD life. I see here 20 master student effort and 10 PhD student effort to make this optical table align. That's crazy. That's so crazy experiments. And then it's like a state of art work. It is well deserved Nature publication. So the whole idea of this photonic quantum computer is based on the photons are identical. Because photons are, if there are like physicists around you, you will know that photons are the vector bosons. And the vector bosons do not interfere. The photons do not see each other if they have different color. So the red and red and blue photons do not interact to each other. The photons only interact to each other if they are identical. So we are using the photon interaction to make the photonic quantum computation. That's why we need an identical single photons. They have to interact each other. So summary, computation, network, secure communication, we all need it. And to realize photonic communication, photonics, quantum photonics, photonics technologies, we need fast photon counters in expensive industry and fast electronics. You have to manipulate the voltage, temperature sources quite fast, and integrating and interference circuits for the photonics. And most importantly, you need an on-demand generation of identical single photons. So how to generate them is a single atom. I told you in the first part, rather for Bohr atomic model. You have an atom, you have an electrons, and you manipulate electrons go up and down. But atoms are hard to work. That's why what we use in semiconductor quantum dots, aka call artificial atoms. So why do we call them artificial atoms? Because semiconductor quantum dots is like a microscopic, still thousands, size of a thousandth atom. It's not that small, okay, couple of nanometer, but still very large, right? You can fit thousands of atoms in a quantum dot, but the whole bulk sphere of the quantum dot acting like a one single atom in terms of electro-optical properties. Because of why? We have a two-level system. When you have a quantum dot, we have a ground state and excited state, the quantized energy levels. And then you give energy to system, electron goes from ground state to excited state, and it comes from excited state to ground state, emitting one single photon every time. That is how we do that one. So last slide, quantum dot, how do we do it and how does it look? So we have a material A, and we have a hole in the material A, and we fill that hole with another material B and cap it with the material A again. So then you have a material B sphere, 5 to 10 nanometer material A sphere between in the material A. So that very small sphere acting like an hydrogen atom in terms of electric and optical properties, and they emit single photon. Here you see one of my samples. There is a 50 micrometer markers on it. Each white dot, you see it in here, one quantum dot emitting single photon all the time. And I collected the photons like I'm making astrophotography for a couple of minutes because I'm getting a one single photon every time. And I accumulated that single photon for a couple of minutes to generate this image, beautiful image in there. Yeah. So, okay, this is like details of that, not that important, which materials we use, etc. Of course, we have to cool them down. Why? Because not something generating temperature. The quantum dust needs to be cooled down to the 4 Kelvin approximately, because we want to suppress the thermal vibration and vibrational noise, phonons, all other things. We want to have a stable environment. We want to have thermally sample is stable and not emitting thermal photons because of blackbody radiation. Then also quantization effect. This quantum effects of this small sphere still getting dominant when you go lower and lower and lower temperature. Here is, you see the crystals that I worked before, lots of different crystals and magnetic fields up to 9 Tesla is kind of, these are stronger than Earth magnetic field and stronger and colder than average space, 1.7 Kelvin. It's like a complex and expensive, complicated devices. Okay, so thanks for listening to me. And as I said, since I'm working on the quantum dots, I said I'll always finish my talks with this Louis Pasteur talk. Science knows no country because knowledge belongs to humanity. And its torch, quantum dot, in my experiment case, illuminates the world. Thanks for listening. I'm happy to answer your questions for another 20 minutes.
Wow, it's really been an incredible session. Thanks, Yusuf. I'm wowed. All I can say is I'm so wowed. And, it's been interesting. And
so I would like to ask you to handle the questions because I didn't like look at the chat, so I leave the moderations of the question to organization.
All right, thank you so much.
You're welcome.
So before question, we like to ask our participants, maybe you can stop sharing your screen for us for just some few
Yeah,
minutes. All right, thank you. So we are asking participants, I mean, from the talk, just share with us your thoughts. And the question is, what one word comes to mind from today's talk? So I'm going to put the link in the chat room. Then the code is also there as well. So just share your thoughts with us before we dive into the questions. All right. So what one word comes to mind from today's talk? So the link is in the chat room. You can use the link, and this is the code 35020811. Wow. So someone says election, quantum, quality, photon, wave function, insightful, cryptography, quantization, quantum dots, mechanics, Marvel, photonic
Marvel was good.
future, cryptography, photon. Yes. Let's hear more from you.
Yeah, I like to
Future.
marvel.
Yes, we want to hear more from you. Technology, quantum physics is the future, quantum communication. Wow. So someone is also wow. Encryption, photons. It looks like now most of us want to be in your lab. So we are thinking about photons and all that. Okay, so as you do this, we'd like to remind you that the recording will be made available to you all on our YouTube channel. So if you have not subscribed to the YouTube channel, kindly do so as well. I'll share the YouTube channel link in the chat room as well. Or Henry, you can kindly share that for us. So inspiring Isaac Newton and all that. All right, thank you so much for sharing your thoughts with us. It's been wonderful. I don't want to say much. I'm just going to allow the participants to ask their questions. So if you would like to ask a question, make a comment, kindly you can use the chat or you can use the raise hand, then you unmute yourself. Thank you so much, Obed. Obed, kindly unmute yourself and let's go.
Thank you very much, Doctors. Thank you, Dr. Karli, for such an amazing presentation. As someone currently working in the cybersecurity space, I have just two questions, actually. The first question is on the compatibility of quantum-like systems on our classical infrastructure. And the second question is also on the entire system of networking. The classical infrastructure has routers and repeaters all around. How does quantum system play a role in this?
Yeah, that's a like a very good question, I should say, because that's actually, if anyone asks me suggestions, so what to look at, this suggestion is exactly the same suggestion that I get like a second July of this year from Alan Aspe in a meeting. He told clearly that I will suggest to everyone asking me what should do, I will say them, go for the quantum network, quantum memories, quantum repeaters. So these are the hot topic. These are the topics that we are working on in Cambridge. And this is a topic that will come, we will see in 1-2 years from a Nature paper from some group, I hope us, but if even if it's not us, it will come from someone. That's the point, yeah. Because the integration of the photonics technologies to the current infrastructure, either we have to make the photons in telecom wavelength, because the photons that I have worked until now was in the visible range. It's like a 718 nanometer. Okay, it's not that visible, but the end of the visible range. But we have to go telecom C-band. So there are groups like Peter Michler in Stuttgart University. Recently, they have shown very good quantum dot sources for the telecom wavelengths. Or there are multiple projects like making the multiplication, like making frequency multiplication for the 800 photons to the telecom band, etc. Lots of things, yes, but we have to go this telecom wavelength for integration the current infrastructure, or we have to go free space. It means we have to go satellites. So we can make quantum network based on the satellite base as well. But in the satellites, I need something repeater, which I call it because the photon sources are so dim, and there is no, I mentioned that there is no cloning, there is no copy machine for the photons, right? But since Obed, you are in the industry, you would know that. What do you do with the normal fiber optic technology? You have amplifiers in how many kilometers? I don't know, but as far as I know, you have lots of amplifiers to amplify the photon signal, laser signal from America to Europe continent, let's say. You have amplifiers, but you cannot use amplifiers for quantum objects because amplifier is actually kind of copy machine, right? And it's not allowed. So it means we have to have repeater. And like repeater means taking the one photon states and making an entanglement swapping and transferring to the other node end. Yes, but these are all state of art. Like this is all like state of art research projects that all Europe is working on, all the world is working on that. Yeah, I would say it's a good point. If anyone wants to in a high impact career, these are the topics now to reach the system. Yes, please.
All right, thank you so much. Obaid, I hope we've answered your question. So
Yes,
is
I
it
just had one more follow-up question.
all right?
So, Dr. Kali, in terms of vulnerabilities, I know that these quantum like cryptography, they don't really secure against like denial of service, and there are also some side channel attacks that I've read about that seem to allow attackers to exploit.
Yes, I have. Let's say if you look at my Google Scholar, you will see one recent paper just uploaded 3 days ago, I think, to archive. We are investigating the side channel attacks for the quantum cryptography system. As I said, quantum cryptography is secure 100% theoretically. If you introduce imperfections, any kind of imperfections on a practical application, that will also make it open to attack. But still, compared to mathematical hardness, this kind of attacks requires more complex system. So to attack a quantum system, you need a laboratory to attack it. That's still more secure. But there's an era of post-quantum cryptography, which I still don't know my side of that. The post-quantum cryptography is also very strong. There are algorithms developed and encryption protocols developed secure against the current quantum computer technology. Instead of going quantum cryptography, one can also propose post-quantum cryptography. But still, as I said, that's still an ongoing war, right? So I don't know yet. Which one is going to be used. Still, we are lacking the quantum computer. That's the missing part, right? So like there is no quantum computer can threaten our encryption industry. We are still far from that. For me, I'm from my field in the photonics quantum computer SWAT. I would say we still need a couple of decades. But I don't know what's happening in the other countries, other group. Maybe tomorrow I will be okay. Someone found the quantum computer can attack any computer. Okay, that might be no problem. I don't want to be like the guy says these computers will not be useful at any time in 1980s, or I don't want to be pessimistic. It can be. It took a couple of years switching us from like the room size computers to the like smartphones took 1 decade. So might be, yeah, I don't know still. Hard question.
All right, thank you. So there's a question in the chat says, can you please elaborate a little on quantum error calculations?
Quantum error calculations, I think we have a different quantum error calculations, but the error calculations in the some quantum computer ones are different what I meant, what the error correction. So for me, the error corrections is I measure a photon, I send 100 photon and I measure 80 photon. And then I have to know, is this loss of 20 photon is expected because of my experimental setup imperfections. So the detector efficiency, fiber coupling efficiency, fiber losses, optical losses, objective losses, electronic losses, etc. So this is one error correction that I meant, but there is another also fundamental quantum error correction, which there is this size of book, which I dare to make a comment on that. That's a very complicated area. So we have to make another talk on that if this is the issue, because what error I meant is the error of the devices, not even error, let's say imperfections of the devices and the corrections of that. Thanks.
All right, thank you. And is there any link between quantum gravity and quantum computing?
There are people, not quantum gravity and quantum computing, but there are people try to work on quantum gravity in Vienna University, Markus Aspelmeyer. This kind of like quantum gravity experiments to quantum optics, not quantum computer. Recently, Philip Walter and his group, one of our previous collaborators, they have measured the Earth rotation by quantum entanglement, much precise than any measurement before. That was one of the first experimental connection between quantum mechanics and gravity. So they have measured the Earth rotation by the entanglement. So you can take their paper in, I think it was an archive a couple of months ago.
Okay, so how will this photonic technology be used in development of materials?
Actually, it's a lot. I mean, the half of the job is materials technology, what we do. Quantum dots, I don't do it. Quantum dots come to me with an DHL express shipping. So the quantum dots are made in this university of Johannes Kepler University in Austria. They are making the quantum dots for us. So I have the molecular beam epitaxy. It's full material sciences. This aluminum gallium arsenide, indium gallium arsenide, etching, it's full material. The latest material technologies are used to generate the quantum dot sample, because we are speaking about here 10 nanometer gallium arsenide sphere inside an aluminum gallium arsenide matrix, which aluminum contribution is precisely controlled, which nanometer and nanometer. I wanted 32 nanometer aluminum 33 gallium arsenide, and I have 20 nanometer aluminum 05 gallium arsenide, and then a couple of nanometer of aluminum 95 gallium arsenide. These are nanometer region of material control made by molecular beam epitaxy. A device seems like coming from a Marvel movie, which is like $1 million of price of such that laboratory. Yeah, that's a strong connection. If the material technologies is one of the where we are limited, we need to get good quantum dot. We need to have a good material control, material engineer, material science to have, first of all, the good quantum dot. I am doing an optics experiment. I need a good quantum dot initially, and that's not in my control. That's related to the quantum dot itself, quantum sample itself.
All right. I would like to remind the participants, you can also unmute yourself to ask your questions. We have another question that says, what are the key advantages of using photons as qubits in quantum computing compared to other qubits implementations?
Yeah, this thing, different platform, superconducting qubits, ion trap. So they have lots of different quantum computer platforms, all using the same idea, as I mentioned, the fundamental physics. They all using this qubit idea, superposition idea. But the photonics one I mean, of course, I'm on the photonic side because first of all, I'm working on the photonic side. That would be that would be not a good statement if I say the superconducting qubits are much better than photonic qubit. But still, photonic qubits are new. They're promising. We have some fundamental challenges. When those challenges are solved, I think there will be an exponential increase in the photonics quantum computer, which is recently it started to hype again. So, but still, personally, if you ask me, the more practical use of quantum computers will come from already very well-known setups, like an ion traps or superconducting qubits. But the quantum networks and the quantum internet and the quantum cryptography, that's all photonics. That's all photonics. So yeah, eventually you need this one, the quantum networks between the quantum systems connection securely. You need photonics. And then photonics computation might be useful for a specific, not for maybe universal computer idea, but it might be very useful for specific calculations because our qubits are very coherent. We do not lose coherence. It's super coherent photon and long-lived coherence in the systems. The only things they are so fast, like generation is so fast, everything is so fast. Electrons are not catching up this fast that enough. That limits the photonic technologies nowadays. The electronic technology is not fast enough.
All right, thank you so much. That's a popular question. People are asking, but it's not showing to all of us. They're asking, how do they get to your lab for
Sorry?
graduate studies? How do they get to your lab for graduate studies? For masters, for PhD
Okay. I mean, that's the
programs?
thing. This like University of Cambridge, and I mean, in the UK, system is more different than the rest of the Europe. So here, I'm a like doctoral researcher. So actually, that's the thing. We have like the research and teaching is here not that connected to each other. So in UK, they have university and the colleges. So that system is kind of different because it's not that you are getting and accepted from a professor like happening most of the Europe. You can apply in Germany and Austria, you can apply a professor and get an acceptance from the professor for its project. So he has a little bit freedom on that. But in UK, it's mostly you have to first pass the University of Cambridge. And then University of Cambridge then accept you, and then you can go for the okay which groups I'm going to work on that and do it. And then you have to find the colleges, and the colleges are like Trinity College, King's College, Queen's College. They all like a different era. So here I say the people most like the UK system is complicated, and they really need to check by university and university, field by field and group by group. It's all kind of complicated. For example, there's a very famous Cambridge Gates scholarships. It started now. If you are thinking PhD in Cambridge, the Cambridge Gates scholarships is one of the most prestigious one, and the applications are open until January. You can apply for Cambridge Gates. They ask you a lot of documentations, etc. Like you should have some already proposal for PhD. I mean, what would you do in your PhD? You should kind of know your field, and you should provide a very good statement. Your past projects, your CV, your cover letter, not written by ChatGPT, like 90% of the text I read recently, clearly written by ChatGPT. So, and then I rather to have grammatically mistaken statements than using a pivotal of states like complicated orchestrates words for the cover letter, etc. So yeah, I think we are at the stage that writing more organic and writing with a mistake is the necessary to not seem like use ChatGPT. Okay, so I can get a couple of more questions. Yeah.
Yeah, your Prince. So Prince, you can ask your question.
Yeah, thank you so much, Dorcas. Thank you so much, Kali. My first question was, of course, how to join your lab, but you just answered that. So I'm going to ask the second question. So how do you explain all this technology to someone who is not yet in the field? Because I believe this is a lot of jargon and yeah, a lot of technical words. So how do you explain this to someone who is not yet in the field?
That's the thing. The science in the 20th century and 21st century is different than the science before. I mean, like before, when people could test the Newton ideas, Newton says, I have a ball, I leave it, it drops. This is something easily, visualize. You can visualize, you can test it, you can do it. But the quantum mechanics and the modern science is so specific. I'm a physicist. Sometimes people ask me questions about this room temperature superconductivity. And I say, I only know the superconductors get high conductivity when you go low temperatures. I'm not an expert on superconductors. I'm not an expert on astrophysics. When they come and ask me sometimes when I walk with my friends here, not physicists, they show me, okay, what is that star? I have no idea what's that star. I maybe will not point to the Jupiter around the moon if it's ever clean. So physics is so specialized. Science is so categorized. It is very hard to explain. But I say people, you should have high quality scientists, not in technical ways. No, we should be good scientists. We shouldn't lie to society. We are spending taxpayers' money. We should be honest. We should tell them what we have directly, and we should make them believe us. The laser, first introduced in 1920s, the first laser has been made was in 1960s. For almost 30, 40 years, there was not even one laser. And the first laser was useless, probably for any technology. But nowadays, lasers are almost the key point of any technology we have. Eye surgeries, I'm not even going for the health industry of the lasers, but the lasers, try to remove them. Then how are you going to use LiDAR sensors for the new generations of smart cars, measure distance, etc.? And then science happening like that. So we are in the now very early stage of the second quantum revolution. It might or might not worthy to spend $1 billion. There's only one way to see that, to progress and wait a time, but not maybe you or me, but our next generations will get the advantages of this quantum technologies, like we are getting the advantages of the tech and of technologies and $1 billion spent in 1940s, 1930s, 1950s, 60s. Then our fathers spent those time and those money on science, and we are getting advantages of that. And it's going to be similar to this as well. So we are going to spend our lifetimes. Maybe I cannot see a fully functional, strong quantum computer advances our technology, but at least I'll be a part of it. And our next generations will get advantage, and they will not remember us. Either we don't remember the guys to make the internet. I always ask this question. The guy found the www protocol, World Wide Web, in the CERN. It was a public open source project. They didn't patent it. They didn't sell it. And no one remembers their name if you don't patent anything. That guy could have been billionaire, probably, if he chose a different path. But then we wouldn't have internet in Turkey, or we wouldn't have internet. Internet would be something, luxury, because it was the toy of some high elite group of people. So I believe science is public, science is open, science is for good worthy. So that's why to develop quantum technologies, I trust the people, and I ask the people to trust us as well. So this will be useful. You will not understand when I explain you. That's a very categorized field of scientific, science. Even I am struggling to understand. And it's very hard to explain someone doesn't know quantum mechanics. This is my like my presentation is the minimum level I can do it. Even if a physicist watch it, it might judge for some sentences I said, as some expert like the previous question asked questions about how imperfect quantum mechanics, you say unbreakable cryptography. Yes, theoretically, but in practically it's a completely different era. It's a like professional field, I will say. Just we should trust a physicist that prove themselves. I mean, I took quantum. I'm doing quantum physics more than 10 years. I have maybe taken every possible courses about the quantum mechanics, and still I'm struggling to understand something. I don't expect the someone is not in physics and quantum physics understand easily as well. But what can I say? That will be the something, one of the biggest invention of the humanity, even bigger than maybe the engine, bigger than the electromagnetic theory, if we can handle it in the future. Okay, so I think I have to stop now. If maybe one more question or not, but in a couple of minutes my door will ring and I have to open it because I'm waiting a Amazon package, which is very important for me.
All right, so I think we just take one more question. So I'll ask, then Wina may ask this question, and that will be all. So what are the current states and future prospects of quantum dots? Then Wina, you can ask your question as well.
Yeah, sorry, I couldn't. Yes, please. I couldn't hear the question.
Okay, the question was the current states and future prospects of quantum dots.
Yeah, I think the quantum dots, I mean, although I think the only bad part of the quantum dots, I would say, they are almost perfect for everything for me, but only thing we have to cool them down, and it makes them expensive and not practical. So the cooling systems, Christ dots are large. It's very hard to make it in like practical device for space applications, etc. So, but nowadays people are trying to make quantum dots and finding a way to control them in some temperatures, like at least like a nitrogen temperature, not a helium temperature. So it's like a 70 Kelvin or something like that. So we can miniaturize it to have some practical compact quantum dot devices. But if you remember that device, it was like Krystad was like the size of me and very, very, very complicated device, right? You don't want to sell that device. You want something practical and compact. Okay, so I have to leave now. Thanks for this invitation. I'm very happy, and you are doing a great job. I think a science shouldn't be forgotten in the other part of the world. It doesn't belong to Europe or the America. That belongs to everywhere, and especially the where that, I mean, the Homo sapiens started, and we started to being human. And then I'm coming from Turkey, the east part of Turkey. Also, I lived in a very, 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 very east part of Turkey cities with lots of different problems, war, things, stuffs, but I didn't lose my passion to science and my hope for the science. I think science will save us if we can, or destroy us. That's important. That's the thing. That's a good gambling. It will save us, either it will destroy us in the future.
All right. Thank you so much.
Thanks.
Thank you.
Thanks. I'm leaving. Have a nice day.
All right. Thank you. So participants, we'd like to remind you to subscribe to the YouTube channel for this talk. If you haven't, the link is in the chat room. And thank you so much for your patience as well, and for your time and efforts, and for your contributions. You have actually made this school a wealthy one for all of us. So thank you so much. We'll continue giving you updates through your mail, then through WhatsApp as well. Finally, stay updated. And the last thing will be attendance. So we'll be sending you your attendance as well to know your efforts and all that. Then you can improve on that. So thank you so much to the team. You've been wonderful as well. Thank you. Have a very great day.